Hey, today we're going to learn about our kinematics equations. Let's get on it. Okay, so one of the most important skills that you'll have to develop in AP Physics 1 is the ability to use kinematics equations to decipher problems, okay? To figure out how an object is moving. So kinematics applies to the motion of an object, and there's basically four things we might want to know about: position, velocity, acceleration, and time. And these equations link these things together. So think of these equations like tools in your toolbox of physics. And these are your core, your main tools. These are your hammers and your screwdrivers of physics. We're going to use these all year long. So it's really important for you to memorize these now. Yes, I said the dirty word memorize. You want it up here. You don't want a paper. Now, they're going to give these equations to you on the AP Physics test, but as an equation sheet. I'm going to do the same thing. Every test, I'm going to give you the AP Physics equation sheet. But you know what? If you're relying on that as a way of solving problems and not having it up here, you've made a huge mistake. I'm just telling you right now. I'm not asking a lot, but memorize those four equations, okay? Now, let's just look at how College Board is going to present them. Now, I'm going to go through each one of these in turn. All right, but one thing I will point out, okay, a couple things I want to point out. One is delta always means final minus initial. So this means final position minus initial position, final velocity minus initial velocity. Okay. The other thing I want to point out is I'm going to use the convention that I prefer, which is using a subscript of I to mean initial and a subscript of F to mean final. That just makes so much sense to me. That's completely intuitive to me. So the change in so final velocity minus initial velocity is equal to the initial velocity times time plus 1/2 the acceleration times time squared. That makes sense to me. Let me show you how College Board will show it to you. So you'll get the equation sheet on the AP test. You'll get it on the test I give you. I will give you their equation sheet. However, take a look at how they do it. Instead of I, they use not. And instead of F, they just don't put anything, right? So if they don't put anything, that means final, right? That's what, see, they didn't put a not there, so that meant final, okay? They also put a little subscript of X with accelerations and velocities to mean like, so you know that these are all in the same dimension, okay? Which is kind of an annoying thing that I think you can figure out regardless. So the thing is, you're welcome to just rely on this equation sheet. I'll always give it to you. However, I think it is uh, disadvantageous to rely on that rather than rely on a memorized set of equations in your head, because those equations are the relationships you need to know. Okay, if you know the equations, you know the relationships, and a lot of the questions really have to do not with calculations, but how well do you know the relationships? If you know the equations, you know them. All right, let's just get on here. Okay. Technically, this is not one of the kinematics equations because kinematics equations apply to objects that are undergoing uniform acceleration. They're accelerating at a constant non-zero rate. This equation I'm including there because it's super useful, especially when we do projectile motion. So this one can only be used if the object is not accelerating. All right, so there's no acceleration involved in this. That's the only time you can use this equation. But there are times when this is very useful. So velocity equals a change in position over time. We've done this one before. This only applies if it's not accelerating. We could expand the delta here to mean final velocity minus initial velocity, because that's what delta always means, final minus initial. All right, let's look at this one here. Now, this is a kinematics equation. I have uniform constant acceleration here is equal to the change in velocity over the change in time. And I could expand that to mean Vf minus Vi. Now, here's something I want to point out. When would I use this equation? Well, if you look at it here, what I don't know anything about here is displacement. There's no X in this, right? So this tool in my toolbox is one I pull out and use. If I don't know anything about the displacement, I'm not asked about it, I'm not told about it, I don't care about it, I would use this one here. And that's an important trick to learn. Like, when should I use it? And the way to do it is look for what's not there. There's no displacement, but it is accelerating. This is the tool you want to use. Now this one here looks a little intimidating, but it's a super useful equation. And if you look at it here, so I have final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. Now notice what's not here, time. So this is the kinematics equation that I'm going to go to if I am not told anything about time or asked anything about time. And it could be expanded. I could just take that delta and change it into this, okay? Now this one here, ooh boy, this one looks like a mess here, right? But basically, this one ties it all together. If I know the acceleration and if I'm told or asked about acceleration and time and velocity and displacement, if they're all coming together, I use this equation here. Now, this one could be expanded because I have a delta, so I could expand this one and say, well, this means final minus initial, so I can move the initial over to this side and write it this way. Okay, just point that out. Sometimes just you want to expand it. But here's what I really want to point out. This equation is a lot simpler and a lot more useful in the special case of an object that starts at a velocity of 0 and then begins to accelerate for a known amount of time, or does the opposite. It's moving, but it comes to a stop. Like if the VI or VF is 0, then you can rewrite it this way. And this equation here, the change in position, how far the object moves, is equal to 1/2 the acceleration times time squared. You will use this equation a bazillion times this year. Learn this one, okay? This is a really useful equation. All right, well, Mr. Sampson, that's way too much stuff to put on a slide. I know, but this is best practice. This is how you should approach a kinematics problems. And I'll be honest, you don't study physics, you practice physics. It's almost silly for me to put the slide here, but I feel obligated to do so. So, really, what you need to do is just start practicing this kinematic problems. We're going to do that when we get into class tomorrow. We're going to be doing that all year, and you will get good at it. And I want to point out, you may not be good at to start with. You probably won't be very good at to start with. You'll probably be thinking, why did I sign up for AP Physics? I made the biggest mistake, Mom and Dad. You didn't. You will learn how to do this. You will get better at this. I've done this a lot, and I know that many of you will start off struggling, and then you will get good at it because you will practice it, and it will just become intuitive to you. It really will. So be patient with yourself. I'll be patient with you as well. So here you go. What you want to do is you first want to make a sketch. It's a simple sketch of the situation. And that's important because it will help you identify the vectors. You're going to use arrows to indicate objects that have a directional component, velocities, accelerations, and displacements. Uh, you want to always try to identify the variable that you're looking for. More on that in a second. So, and just say like, oh, I'm looking for final velocity. So V final equals question mark. Uh, you should decide which direction you want to set as positive. Now, if we don't have any reason to do otherwise, it's simplest to say right is positive, left is negative, up is positive, down is negative, and just go with it. Okay, that's the safest way to do it. However, there are times when I know I'm just dropping rock and it's just going to fall straight down. It seems kind of silly to say, well, it's got negative displacement and negative acceleration. If it's never going to go in a different direction, why bother with a negative? So it's up to you to choose which direction to put as positive. That you could choose down as positive if it's going to simplify your efforts. You'll get the same answer either ways, but you just have to keep track of negative signs a little bit more. So then make a list of all the variables that you do know, and then basically pay attention to which one you don't know or don't care about, and that will direct you as to which equation to use. So once you've made that list of known and unknown variables, then you're going to use that to choose the right kinematics equation. It's usually a good idea to rearrange that one to solve for the final one before you substitute any values. You'll notice with me, I tend not to do that. It's I guess it's one of my little faults, but it's the way I am. And then you substitute those known values. And here's the thing, I put it in bold for a reason. You really need to be careful with negative signs because we're dealing with vectors here and they're not always in the same direction. And when you make mistakes, 9 times out of 10, 99 times out of 100 is because you screwed up a directional indicator. You put a positive when you meant to put a negative. That's usually what happens. And the last thing I'll say is just remember that when objects fall, and that's it's a standard thing we do. We don't say like the object is falling. We don't say, and by the way, it's accelerating. You're supposed to understand if an object is falling, it is accelerating at 10 meters per second squared in the negative direction if down is negative. But maybe you're going to call down the positive direction. So the main thing is it's falling in the downward direction. But understand if something is falling, it is accelerating at 10 meters per second squared, which is also 9.81 if we were doing a lab and we want to be uh, more precise. Okay, now the interrogative word. There's going to be a word in a problem that makes it a question, and that's going to tell you what variable it is you're trying to solve for. And that's a really important thing to know, right? That helps you decide which equation to use. So let's just pay attention to this. So think about the words that are associated with what you're trying to find. So if you hear, when will this happen? I'm looking for time. If I say, how long will it take for this to happen? How long until? I'm talking about time. by the way, how long is not, we're not talking like a rope. I mean, something might say how long is the rope, okay, but usually we're saying how long, meaning the time. If I say where something is, I'm looking for position, or how far did it go, or how high was it dropped from, or how high did it go. Then I'm looking for position. How fast is usually velocity or speed, is the rate of displacement. But sometimes we say how fast does it accelerate, in which case I'm looking for acceleration. Or a lot of times we'll just say what is the acceleration. So pay attention to those interrogative words because they tell you which variable you're trying to solve for. Let's just do an example, okay? An arrow is fired vertically upward at 40 meters per second out of window A at 25 meters above the ground. At a later time, the arrow is observed to pass by window B at a velocity of 15 meters per second in the downward direction. How high above the ground is window B? Whew, okay, well, first thing we do is we're going to draw a sketch. Here's my sketch. Here's my building. Here's my arrow going up. Here's my arrow coming down. And now I'm going to start labeling my variables. I know that the arrows start off at the initial position. So xi, I'm going to call it x, even though that's the y direction. So the initial position was 25 meters above the ground. Now notice I made that positive. So I've chosen to use up as positive and down as negative, which is what we're usually going to do, but not always. The arrow is fired at 40 meters per second upwards. So I'm going to make that positive 40 meters per second is VI. I also know that the final velocity is in the downward direction at 15. So I'm going to say negative 15 meters per second is the final velocity. I also know, even though I wasn't told this, that things fall under the influence of gravity. So that means I have to remember the object is accelerating, and therefore it's accelerating in the downward direction, which I decided is negative at 10. So it's negative 10 meters per second squared. And the question was, how high? So I'm looking for a position. The final position is XF. Now I am ready to do my job here. So the first thing I need to do is I say, all right, oh, I just did all that. Never mind. Okay. So I'm going to look at the different equations I have, right? This one's out because this one only applies to situations where there's no acceleration. This one isn't going to work because I don't know anything about time. I wasn't asked about time. This one's out, again, because time. I don't know anything about time. So that leaves me with this one here. I wasn't asked about time. I don't know about time, but I do have velocities. I'm looking for displacement, and it is accelerating. So I'm going to take this equation. Since I'm looking for the final position, I'm going to expand it out, and I'm going to rewrite it to solve for this. Again, I often don't do that. Sorry, but that's what you should do. Okay, and then I substitute in. You got to be really careful when you substitute in because of negative signs. Now, it doesn't really matter this negative here because I'm squaring it anyway, right? Negative times negative is going to be positive. But negative 15 meters per second squared minus 40 meters per second squared divided by 2 times the acceleration, which, by the way, is negative acceleration, plus a positive displacement for, positive position for x1, 25 meters above the ground. And then when I solve this, I get 93.75 meters is the final position, and that's a positive value above the ground. Does this make sense? It does. If I ended up with a negative here, I got or if I got something like thousands of meters, like you should always evaluate this and say, does this make sense? And if they don't just slavishly accept it. If it doesn't make sense, it doesn't make sense. You got to go back to the drawing board. All right, let's try one more. Okay, and then I'll shut up. Okay, so a person fires an arrow upwards and 7 seconds later, it hits a bird. Sorry if that's a violent example. That's 105 meters above him. How fast was the arrow going when it left the bow? Okay, well, let's just make a sketch of it. Maybe then it'll all start to make sense. Okay, so I make my sketch. Here's my bow. Here's my arrow. And here's the bird up above it, kind of in profile here. And I've got, all right, from behind, I guess. Uh, and and I know that the bird was 105 meters above me. I chose to set up as positive and down as negative, so I'm going to make this a positive position. Actually, is a displacement, so I don't need a final velocity because I got a final position because the initial one is I'm going to call it 0. So I could have put this as delta x if I wanted. I know that the time was 7 seconds. It's in the air and there's gravity, so I have an acceleration and it's in the downward direction, so it's going to be negative 10 meters per second per second. And what I'm trying to find is the initial velocity of the arrow as it came out of the bow. That's what I know. All right. So basically, I have position, time, acceleration, velocity. I have to use this equation. All right, that is the equation I'm going to use. So let's go ahead and rearrange it for initial velocity. So if I arrange it for initial velocity, it takes this form. Again, a lot of times I don't do that, but I should. I'm going to substitute the values in, being very careful with my negative signs. So 105 uh, meters of displacement minus 1/2 a, and a is negative 10, times the time squared over time. And then that's going to give me my answer. And when I solve it, I get 50 meters per second. That seems pretty reasonable. All right. But what if I had forgotten to use, say, negative 10 for gravity? Well, if I'd forgotten that, I would have gotten negative 20 meters per second. So it would have been in the downward direction. It's like, that really doesn't make sense. All right. So always look at it afterwards and actually if it makes sense, and be very careful with those negative signs. Okay, last thing is using proportional reasoning with kinematics problems. This is something we often have to do. So when a rock is dropped from rest from a height h, it hits the ground at time t. How long would it take the rock to hit the ground if it was dropped from height 3h? Oh my God, you will get a question just like this on the test, I assure you. So let's think about this here. How do we approach this? Well, the object is dropped from rest from a particular height. So it travels a certain position from one position to another. It is accelerating because it's falling, and I know time. It started from rest, so I can use this equation. I'm telling you, you're going to use this equation a lot. So basically, now that I've got this, I say, all right, I can rearrange this to see, since I'm only asked about height and time, acceleration and this 1/2 don't matter, right? So I'm going to say time is proportional. It really should be a proportional sign to the square root of h, because if I rewrite this, this is delta h, or the height really, all right? And I try to solve for t, I'll get this. So now, if that's the case, then if I triple the h, what happens to the time? Well, the time should go up by root 3. So the new time should be root 3 times the original time. All right, let's try another one. A rock is thrown up with initial velocity v. It reaches a height h. How high would the rock go if it had been thrown up at velocity 2v? I'm telling you, they love to ask these kind of questions. You know what I don't have here? I don't have time. I know what equation I'm supposed to use. I'm going to use this one here. All right, this is the equation I want to use. Now, if it didn't change in proportional reasoning, if it didn't change, I'm not going to worry about it, right? So let's first of all, when it reaches height h, the final velocity is going to be 0. Agreed? All right. So if I make this 0, then I'm going to rearrange the equation. And what I get is vi squared equals 2a delta x. And really, it should be a proportional sign because I'm only interested in the velocity and the height. So this I'm just going to set equal to 1. It doesn't matter. So what I know is v squared is proportional to delta x. Now the question is, if I threw it at 2v, so if I put a 2 here, 2 squared 4, it should go 4 times higher. That's how we do it. Okay, thank you for watching. I know this is a long one, but it's an important one. See you in class tomorrow. We'll get to work on it.